Hey, what's up guys? Thanks for tuning in. Today I'm introducing the Nucleus-Alchemiac, which is our first product that goes onto the market. So yeah, it's a new BCI device that comes into the market. So what's the idea here? Do we need another BCI device? Well, at least my opinion is that we can afford a new one. So the Nucleus-Alchemiac was developed with a few ideas in mind. To put it shortly, this is my dream device. This is a system that I've been thinking about for a very long time. I've been working with brain-computer interface for well over 10 years now. And this is a device that really encompasses what I was seeing, what I need, and what I was seeing as being a set of useful features for BCI to be put on the market. So here it is. I'll give you like another shot at it in a few seconds. But basically the idea is that I wanted a system that is full featured. I'll show you the next slide, everything that is on this board. A very small form factor, very essential to me. I've been working with other devices on the market, but this one is, as far as I know, it's the tiniest, or at least within the affordable, accessible systems and hackable, it's definitely the smallest or one of the smallest. And I wanted a system that is hackable. But the idea is, if I roll back, back when I started with brain-computer interface, or at least with consumer-grade brain-computer interface, there was a few devices on the market that was very accessible for hackers. And what I've noticed is that this door has closed. Most devices on the market right now are much more expensive than they were. And I've wanted, given that I need this device for my own purpose, what I've wanted is to give back to the new generation of hackers and to give you guys a device that you can afford, that you can play with, that you can build maybe some hacks around it. So this is the idea. I wanted something that is hackable. When I say it's full featured, so basically the idea, so what it has, it's an 8-channel device. Of course, it's not like a high-density system. It's not a 16-channel, but 8 channels is good enough for many, many applications, or at least that's sufficient for what I'm working on. It has 9 degrees of freedom, so it has a gyro, it has compass, accelerometer, so it can really track, the movements of the body part where the system is installed. In this case, the idea is I want a system that is wearable on the head, so you can track head movements. There's 2 buttons, 2 LEDs on board, so they are configurable. You can do whatever you want with them. You can use them to send maybe tags or to stop some operations. So it's as you wish. And the LEDs are mostly thought as a monitoring system, so you can see the status of the device when you're using it. There's 2 extra ADC. Right now, they're not being used. In the future, I see them being used maybe for PPG, so to capture heart dynamics, or for skin conductance, which I use great metrics. I use them usually with a wristband, but it could be nice to have them as extra inputs. But right now, it's simply 2 extra ADC that are left there if you want to use them for something else. There's several GPIOs that are available. The system connects over BLE, and the idea with Bluetooth low energy is that it's low energy, but also it makes it possible to connect with smartphones, connect with PC computers, Linux, so everything is connectable, super easy to work with, and it's been tuned and validated to provide a 0% packet loss. Conducted some tests. It's a very reliable link, doesn't require an external dongle, so it's a great connectivity approach and a reliable one as well. So that's kind of like the features that this system has. We're also going to release it with open firmware, open SDK. Firmware obviously it's good. It's a good thing to say it's open. It's a different thing to program the chip and everything. But we actually we've integrated a very standard interface. So all you need is this programmer here, which is USB. So it's a ST-Link V3 Mini E, and you see it's just like a connector like that, and you can just connect it and program the device. It's super easy. All the software to program it are freely available. Open SDK, so all SDKs, Python for smartphones, so everything is going to be available as open source. We will support official release, but we encourage the community to build whatever you need, guys. And the whole system is going to be licensable. I think it's a nice thing to know that if you want to build a product or something around it, we'll happily sell you a license, and then you can use it for whatever you want. So the idea here is really, this is, for me, it's a passion, it's a thing I'm building. And if it can benefit the community of brain-computer interface hackers, then the happier I am. So I wanted to give you a proper view of the Nucleus-Alchemiac. You can see the board right here. Just to show you the size, here's a OpenBCI Cyton with the DAISY module, just for comparison. And as you can see, the area that is covered by the device here is much smaller. So this is meant to be embedded in head wearables. The device is made of two main components. So you have the base board and you have the breakout board. The breakout board provides the connectivity for 8 channels, the bias, the reference, as well as one GPIO is available here with its ground on the 2 pins here. But you also have access to a bunch of ground, power, and more GPIOs on the through hole here, so it's easy to hack with. The baseboard is the component that integrates everything. So you have the microcontroller here, you have the ADS1299 all the circuitry. It also has 3 buttons, so this is the reset for the microcontroller, and these 2 are user-defined functions. You also have 2 LEDs right here, again, user-defined functions. The idea, why is it made in 2 components? Well, there's 2 ideas. One was to reduce the footprint of the whole assembly, but the other idea is that the breakout board here is meant to be interchangeable with other breakout boards. This is the one we've made for our specific requirements. So we have our micro FL connectors here that we use on our other product, the Nucleus-Hermès. And the idea is that if you build a system around the baseboard and prototype with, let's say, this version of the breakout board, well, you only need to replace technically the breakout board to adapt to a new connectivity interface. The system is battery operated. In this case, we've integrated a 45.6 module that you can find on Amazon. This integrates a charging module as well as the battery management interface. Now, I mean, this is a quick hack. You have like the little switch here. Obviously, this is not meant to be permanent. The Alchemiac consumes roughly 35 milliamps, and on this system here, we've installed a battery that is 300 milliamps hours. So it gives you an idea that we have probably around 7 or 8 hours of operation with this very small package. So this is it. This is the Nucleus-Alchemiac. It's probably, like I said, probably one of the smallest devices on the market, at least in its price points. And the goal is to make it as hackable as possible. The device can also be easily reconfigured. So as we said, we provide several extension functionalities. There's a connector right here that is meant for a programmer. So you see you have the ST-Link programmer right here, and it's pogo pin connector. So all you need to do is to pop it like this, and then you can reprogram the chip very easily. This is accessible, and all the software required to reprogram it are freely accessible. So this is it. This is the Nucleus-Alchemiac. Back to the demo. All right, so the demo today. So as I'm building the firmware, I need to validate it. I need to make sure that everything works. I need to develop it, run some tests. And over the time, discussing on the web and everything, there's been a lot of question about one feature in particular, which is called the bias circuit. And I thought that it could be an interesting way to introduce the device, to also take the opportunity to explain what is the bias, how it works, introduce also the chip, the ADS1299, which is the analog to digital converter on board. So before proceeding with the bias demo, the ADS1299 is the analog to digital converter, ADC. It is the gold standard for biosignal measurements. Most BCI on the market use this chip. Like, it's a SoC, system on chip. It integrates multiple functionalities. It's a great system, a little bit expensive. Otherwise, it's a great system. And most devices I can think of, I think about the OpenBCI Cyton. The ganglion is different. The OpenBCI Cyton, the M-Brain Train. Every time you see a system that says 24 bits with a gain of 24, is usually because it's used ADS1299. There's a way to build a BCI without this chip, okay, but then it gets a little bit more complex in terms of hardware engineering to build your system. So the goal today is to take the opportunity to address one specific feature, which is the bias circuit. People have a rough idea of what it does. People understand that it reduces noise. It uses the common mode signal rejection method, but how it works exactly, this is what we're going to be looking at today. So the first thing I want to jump into, so this here is the data sheet of the ADS1299. It comes with 4 channels, 6 channels, 8 channels. 8 channels the most used. It's extensive documentation. The most important parts, if you ask me, I think the schematics are where you want to start. It tells you a lot about how it can be configured. So this is an overview here. This is the 8-channel configuration. Each channel has a positive and negative electrode. We see here the SPI interface. The SPI is how this device is connected with the microcontroller. So it's a serial link. I think I have a nice demo that we can do with seeing the SPI in action, but it won't be today. The RDY that plays a role here by being used for the interrupt, to drive an interrupt and tell that the new sample is ready. We can see here that this is the digitalization step. So this is a delta sigma analog digital converter. It's a great system to do this conversion. What the delta sigma does is it actually oversamples and filters the signal before turning it into a digital signal. It's an important step because it helps to prevent things such as aliasing. Aliasing is when a frequency higher than half your sampling rate goes through your signal and then reflects into lower frequency bands. So this is a great approach here to build a low noise analog digital converter. We have here the gain, programmable gain, and the pairs of electrodes here. And then this is the configurable part. It's a MUX for multiplexer. It's a gating system that you can use to configure how the various inputs behaves, and we will be playing with the MUX extensively today. This is the map of the MUX here. You see figure 18. It's a little bit overwhelming when you look at it at first, but when you get into the details, you look at the registers and everything, you don't play with all the switches all at once. You work only through a few of them. Today, the first thing I want to look into, okay, so we're going to be doing, the demo will be in 2 steps. So the demo will follow 2 steps. The first thing I want to demo is the stream mode. The stream mode happens as part of the startup sequence. The startup sequence is defined in the data sheet on page 62, figure 67. It's a series of steps that you go through to ensure that the device works properly. Amongst other things, we issue a reset pulse just to make sure that the device, after power up, you reset it just to make sure that it is in its right state. We send a few commands. We set up all the electrodes in input short, just to make, so it means that they are actually not connected. This is a intermediate step. What we really want to get to is here we go and set up the test signal, and you see in the data sheet we tell each configuration what needs to be done, each register, how they need to be configured. Technically, what we do at this step is we activate the test signal. Okay, by activating this bit here, we say that the test signals are driven internally. This is what starts the generator. We set up the gain and set the test signal. So the only thing I changed here is in configuration here, the gain is set to 1. I changed it to have a gain of 12 to be more in line with what how I expect to use the device. And you see we activate the test signal here. So by changing this bit and these ones here, what we do effectively is we close the switch here for the test signal to be connected, and we close this switch here. You see the 101 here, such that it connects the test signal all the way to the programmable positive gain here. Okay, so this is how we set up the test signal. So what I have here is a Python script, okay, that connects through Bleak, that will interface with the device. It will set up a display where we see all the channels. So what I'm doing, I'm powering up the Alchemiac, powered up. Now I can start the script here. Okay, let's see, we're scanning for the bias. It shows up. I haven't changed the name yet from the example program that I'm using. So to connect, and you see we have the test signal working properly here. Test signal are those square waves. They're all synchronous, and this tells you, this is an important state because it tells you that the ADS1299 can be configured properly. It tells you that it connects with the microcontroller properly, and further it tells you that it transmits over BLE properly, and that the way you decode the information on the side and scale it works properly as well. Also, it works at 250 hertz now, and actually I have message. If I'm losing message, if I'm dropping packets, I have warning. So you see here, so I'm not dropping any packets, and it's just an important state that shows you that everything works well. The second part of the demo now is to show you the bias. So what I've done is I've configured the firmware such that when I press the button, it executes this sequence here, where it configures the system differently now, such that, and it's a little bit of an interesting trick. So what I do here, so this is the bias circuit. The bias is this op amp here, okay? It's configured to output a signal. There's a filter here before it feeds back in the negative pin. The plus pin, the plus of the amp here is set to be assigned to the AVDD plus AVDS divided by 2, which technically is very close to 0 volt. And the circuit that you see here, this is where the bias is interesting, is that all channels can be fed into the bias. This is the common noise rejection. So you can take all your input. You see, this is the programmable gain for 2P. You can even bring the negative pins, 4P, 3P, so all of them can be fed into a summation circuit, and they get fed into the negative. So the more they sum up, the more it's going to output negative, and this is actually connected to the skin. Okay, so you see, so it sends the inversion of the signal. Now the demo that I'm doing is, I'm doing a little bit of a trick here. So I'm activating the test signal on all pins, the test signal. I'm powering up the bias op amp, and all channels are connected to the test mode, but the channel 1. And what I do is I close all these switches here, all but the first channel. Okay, and you will find this here. You see in XP, so all the P's connected to bias, but the first one, the one is still left open. Okay, and you see channel 0 is set to 6.0, and all other channels are set to 5.5, which is a test signal. And what I do is I have electrodes connected, and what I do is I feed back the bias signal back into channel 1. Okay, so this is the trick that I'm doing. So you see it happen. So first here, I'm pressing the button to change the configuration. So I press the button, and hope you see all channels are still behaving the same, but channel 1 here becomes something else. Currently it's floating, so it's just like connected to whatever. You see, if I move the channel, we should see like a lot of noise on it. Or if I keep on touching it like that, maybe. Okay, so it's just floating. But now if I connect it to the brown here, which is the bias, okay, you see now we have it. And what's interesting here is if we take a screenshot, okay, and look here, what's interesting is that when this one here goes down, this one goes up. Okay, so what we find is that all signals, all channels are going down, they get summed up, they're all in sync. And what is fed back from the bias is actually in opposite direction. So when all channels goes down, the bias tries to cancel out this effect by going back up. Now, this is a little bit of so that's an interesting. So it shows indeed that the bias tries to output the opposite of what is fed in. Now, this little thing, we're kind of lucky because here I kind of cheated a little bit the system. It's not connected the way it should. Okay, when I say it's not connected the way it should, is because here it's shorted directly, and that here we have an infinite input. Not infinite, but we have a very high input impedance. There's actually no current going through here. Kind of mess up a little bit with the circuit. But if we connect the reference, we'll see that the behavior will change a little bit. And what we find here is that you see it doesn't try to effectively cancel the whole signals. What it does is it only tries to cancel, or at least it's only effective at the onset of a transition here. The reason for that is that if you look at a test signal here, okay, this is 5 seconds history. Give or take, okay, the time of one cycle is, if you take a look at it, it's roughly 1 second. So it means that the square wave here has a 1 hertz frequency. 1 hertz frequency is a very, very low frequency in the world of signals. In terms of biosignals, it's on the lower end of EEG, but it's still like considered like in signal processing a low frequency. Now, the reason why it's only active on the edge here is because of this filter here. Okay, so the bias doesn't try to cancel all components of the signal, but it's tuned. It's tuned to reject. In this case, the circuit is configured to be a high pass. So this is an active high pass filter, and what it does is the bias will only try to cancel high frequency content. When we have a square wave like that, okay, there's actually a lot of frequencies that are involved in this signal, but the edges contain a lot of high frequency elements, and this more of a low frequency of square wave. This is a very low frequency, and this one, the bias actually doesn't register it, doesn't try to cancel it. It only tries to act on the edges of the signal. So this is what we see here. And whenever I whenever I mess up with the circuit, we find back the square wave. But when it's configured properly, connected properly, it should only try to cancel out the edges of the signal. Okay. The goal today was just to show you a little bit of where I am. I mean, we still have a lot of development on our end before getting everything to work, but the idea I wanted is just to take the opportunity to explain a little bit of how the bias circuit works, okay, how to work with the ADS1299 by configuring the registers, and the test mode also with the ADS1299 is an important configuration when you want to validate your system. I hope this answered a few of your questions in regard to what the bias circuit does, and this is it. That's it. Thanks a lot. Bye.